Quantum physics is the study of the smallest layers of reality. At first, it seems distant, almost abstract, something far removed from everyday experience. But as we look a little closer, it begins to feel strangely familiar. The world we see, the objects we touch, and even the thoughts we hold are all shaped by processes unfolding quietly beneath the surface. In classical thinking, reality appears solid and predictable. Objects have clear positions, causes lead to expected effects. But in the quantum world, this clarity begins to soften. Particles do not behave like tiny solid pieces of matter. Instead, they exist as gentle patterns of possibility, shifting and unfolding in ways that are not always certain. Take a moment to imagine this. Not a world made of fixed objects, but a world made of probabilities. A place where something can exist in many states at once, where outcomes are not decided until they are observed. It may feel unfamiliar at first, but there is a quiet rhythm to it, a subtle order that reveals itself with patience. Quantum physics does not replace reality. It deepens it. It suggests that beneath everything we experience, there is a layer of softness, a structure built not on certainty, but on possibility. This idea can feel unsettling, but it can also be calming. It reminds us that not everything needs to be fixed or fully known. Wave duality is one of the most gentle and surprising ideas in quantum physics. At first, it seems simple. Something is either a particle or a wave. A particle is like a small object with a clear position. A wave is something that spreads out, like ripples moving across water. These two ideas feel separate, almost opposite. But as we look closer, this distinction begins to soften. In the quantum world, light does not behave only as a wave, and it does not behave only as a particle. It behaves as both. This is often called wave-particle duality, a phrase that quietly challenges the way we understand reality. Take a moment to imagine a calm surface of water. A single drop falls, and ripples begin to spread outward in smooth, circular patterns. The wave does not exist in one place. It exists across space, gently expanding. Now imagine a small grain of sand falling instead. It lands in one place, fixed and defined. In everyday life, these two behaviors are separate. But in quantum physics, something unusual happens. Light, and even tiny pieces of matter like electrons, can behave like both the ripple and the grain at the same time. This idea first became clear through a simple but profound experiment. When light passes through two narrow openings, something unexpected occurs. Instead of forming two simple bands on a surface behind the openings, it creates a pattern of light and dark stripes, like overlapping waves. This is known as an interference pattern, a gentle signature of wave behavior. But here is where it becomes more subtle. If we send light through the openings one small unit at a time, as if releasing individual particles, the same pattern still forms. Each small unit seems to arrive as a single point, yet over time, a wave-like pattern quietly emerges. It is as if each particle carries within it a hidden wave, a range of possibilities about where it might appear. Take a moment to reflect on this. Something that appears to be a single object also behaves like a spread-out pattern. It does not move along a single path, but along many possible paths at once, gently overlapping with itself. This can feel difficult to picture, but there is no need to force clarity. Instead, imagine a soft cloud rather than a sharp point. A cloud does not have a precise edge. It drifts, expands, and changes shape. In a similar way, quantum objects are not always confined to a single position. They exist as distributions, quiet spreads of probability. Another fascinating aspect of wave duality is how observation influences what we see. When scientists attempt to observe which opening a particle passes through, the wave-like pattern disappears. Instead, the result becomes more particle-like, forming two simple bands. The act of observing seems to guide the behavior, gently shifting it from wave to particle. It is not that the particle changes its nature suddenly. Rather, the full range of possibilities becomes more limited when we interact with it. The system settles into something more definite. This invites a deeper reflection. In everyday life, we often assume that things exist in a fixed way, independent of how we look at them. But wave duality suggests something more subtle. It suggests that the nature of reality is not always fully determined until it is experienced or measured. Take a moment to imagine paths spreading out before a traveler. Instead of choosing one path immediately, all paths exist as possibilities. Only when a step is taken does one path become real, while the others quietly fade. Wave duality carries this gentle idea into the fabric of the universe itself. It also reveals something about the limits of intuition. Our minds are shaped by everyday experiences, where objects are solid and predictable. But at smaller scales, reality does not follow these familiar patterns. It becomes softer, more fluid, and more open. This is not a flaw in understanding. It is an invitation to expand it. Wave duality is also deeply connected to the mathematics of probability. Instead of describing exact positions, quantum physics often describes likelihoods. It tells us where something is likely to appear, rather than where it must be. Over time, these probabilities form patterns, just as individual drops of rain can form a river. This perspective can feel calming. It suggests that uncertainty is not chaos, but structure in a different form. A structure built from possibilities rather than certainties. Each outcome is not isolated, but part of a larger pattern that unfolds quietly and consistently. Wave duality also appears in technologies that shape the modern world. Devices that rely on the behavior of electrons, such as tiny circuits and advanced sensors, depend on this dual nature. The same principles that seem abstract and distant quietly influence the tools we use every day. Yet beyond its applications, wave duality offers something more reflective. It reminds us that identity is not always fixed. Something can hold multiple aspects at once depending on how it is approached. What appears simple on the surface may contain layers beneath, gently interacting in ways we do not immediately see. Imagine again the ripple on water. It spreads outward, overlapping with other ripples, creating patterns of light and shadow. No single point defines the whole. The pattern emerges from interaction, from movement, from possibility. In the same way, the quantum world is not built from isolated points alone. It is built from relationships, from overlaps, from quiet combinations of paths and outcomes. Take a moment to rest with this idea. A particle is not just a point. A wave is not just a spread. Each contains something of the other, blending in a way that challenges simple categories. This blending is not chaotic. It is gentle and structured, guided by mathematical patterns that describe how probabilities evolve over time. These patterns are consistent, even if they are not always intuitive. Wave duality teaches us to become comfortable with this softness. It invites us to let go of rigid distinctions and to allow for a more fluid understanding of reality. It suggests that the world is not always one thing or another, but sometimes both, quietly coexisting. The uncertainty principle is one of the most quiet and profound ideas in quantum physics. At first, it may seem like a limitation, a small gap in our ability to measure things precisely. But as we look closer, it reveals something deeper about the nature of reality itself. In everyday life, we are used to clarity. We expect that we can know where something is and how it is moving at the same time. A car on a road has a position and a speed. A ball in the air follows a clear path. These ideas feel natural, almost effortless. But in the quantum world, this certainty begins to soften. The uncertainty principle tells us that there is a limit to how precisely we can know certain pairs of properties at the same time. The most well-known example is position and momentum. Momentum is a way of describing motion, combining both speed and direction. If we try to measure the exact position of a particle, its momentum becomes less certain. If we try to measure its momentum very precisely, its position becomes less clear. This is not because our tools are imperfect. It is not because we need better instruments or more careful techniques. This uncertainty is built into the structure of reality itself. Take a moment to imagine trying to observe something incredibly small. To see it, you must interact with it, perhaps by shining light upon it. But the act of shining light is not passive. Light carries energy. When it touches the particle, it gently disturbs it. The more precisely we try to observe, the more we must interact. And the more we interact, the more we influence what we are trying to measure. This creates a quiet balance. To know one thing clearly, we must accept uncertainty in another. It is as if clarity in one direction creates softness in another. Imagine trying to focus on a single point in a dark room. As your attention narrows, everything else fades. The details around the edges become less defined. In a similar way, the quantum world does not allow everything to be sharply known at once. But the uncertainty principle is not only about disturbance. It is also about the wave-like nature of particles. Earlier, we explored how particles can behave like waves, spreading out across space. A wave does not have a single precise position. It has a range, a distribution. The more tightly we try to confine this wave to a small region, the more its motion becomes spread out. This relationship is gentle but exact. A tightly localized wave requires many overlapping wave patterns, each with slightly different motions. These combine to create a precise position, but at the cost of a wide range of possible momenta. On the other hand, a smooth and extended wave has a clear and consistent motion, but its position becomes less certain. This is the quiet mathematics behind the uncertainty principle. Take a moment to reflect on this balance. Precision is not absolute. It is shared between different aspects of a system. To gain clarity in one dimension is to release it in another. This idea can feel unfamiliar, but it carries a certain calmness. It suggests that limits are not failures. They are part of the structure of things. They define what is possible, guiding the way reality unfolds. The uncertainty principle also invites a deeper philosophical reflection. In everyday thinking, we often seek complete understanding. We want clear answers, definite outcomes, and stable truths. But the quantum world gently reminds us that some aspects of reality are not meant to be fully pinned down. There is always a softness, a space where possibilities remain open. Imagine holding water in your hands. The tighter you try to grasp it, the more it slips away. But if you hold it gently, it settles, flowing naturally without resistance. In a similar way, the quantum world resists rigid certainty. It invites a softer approach, one that accepts partial knowledge and quiet ambiguity. The uncertainty principle also plays an important role in the behavior of atoms and matter. It prevents electrons from collapsing into a single point within an atom. Because their position and momentum cannot both be precisely defined, they remain spread out, forming stable patterns around the nucleus. This gentle uncertainty is what allows matter to exist in a stable form. Without it, the structure of atoms would be very different, perhaps even impossible. So what appears at first as a limitation is actually a foundation. It creates space, structure, and balance within the smallest layers of reality. Take a moment to imagine electrons not as tiny particles orbiting like planets, but as soft clouds of probability shifting and adjusting within invisible boundaries. Their motion is not fixed, but guided by the interplay of uncertainty. This image is quieter, less rigid, and perhaps more calming. The uncertainty principle also extends beyond position and momentum. There are other pairs of properties, such as energy and time, that share a similar relationship. The more precisely we define the energy of a system, the less precisely we can define the time over which it exists. This creates a world where even existence itself can be fleeting, appearing and fading within brief moments. Again, this is not chaos. It is structure, expressed in a different form. A structure where precision is balanced, where certainty is shared, and where limits create possibility. As you continue to reflect, allow this idea to settle gently. There is no need to resolve every detail. Just notice the pattern. A world where knowing is always partial. A world where clarity and uncertainty exist together, not in conflict, but in quiet harmony. Quantum superposition is one of the most gentle and mysterious ideas in quantum physics. At first, it may seem difficult to accept. We are used to thinking of things as being in one state at a time. A light is either on or off. A door is either open or closed. These clear distinctions feel natural and stable. But in the quantum world, this clarity begins to soften. Superposition suggests that a particle can exist in multiple states at once, not switching rapidly between them, but quietly existing in a blend of possibilities, all at the same time. It is not one outcome or another. It is many outcomes, gently overlapping. Take a moment to imagine a simple choice, a path that splits into two directions. In everyday life, you would choose one path and leave the other behind, but in superposition, both paths remain possible. The system does not commit immediately. Instead, it holds all options together in a quiet balance. This idea becomes clearer when we think again about waves. A wave can spread out across space, existing in many places at once. It is not confined to a single point. In a similar way, a quantum system can exist in multiple configurations simultaneously, like overlapping waves of possibility. Only when something interacts with the system does one outcome become definite. This interaction is often described as measurement. But measurement here is not just looking. It is any interaction that brings the system into contact with the environment. When this happens, the superposition gently resolves into a single state. Take a moment to reflect on this transition. Before interaction, there is openness. After interaction, there is clarity. The shift is not violent or sudden in a dramatic sense. It is quiet, like a ripple settling into stillness. To understand this more deeply, imagine a musical chord. When several notes are played together, they form a harmony. Each note exists within the whole, contributing to the sound. You do not hear just one note. You hear a blend. Superposition is similar. It is a combination of states, existing together in a structured way. When a measurement occurs, it is as if one note becomes isolated, while the others fade into silence. But before that moment, the full harmony exists. This perspective can feel calming. It suggests that reality is not always forced into immediate decisions. There is space for possibility, for multiple outcomes to coexist without conflict. Superposition also plays a key role in how quantum systems evolve. Instead of following a single path, a system explores many paths at once. These paths can interfere with each other, reinforcing some outcomes while cancelling others. Over time, patterns emerge from this interaction, guiding the probabilities of what we eventually observe. This is not randomness in the usual sense. It is structured possibility, shaped by underlying patterns. Take a moment to imagine light passing through multiple paths at once, gently overlapping and creating patterns of brightness and shadow. Each path contributes, even if it is not directly seen. In the same way, all possibilities in a superposition contribute to the final outcome. Another way to think about superposition is through balance. Instead of being fixed, a system remains in a state of potential. It is not undecided in a confused way. It is open in a structured and meaningful way. This openness is a fundamental feature of the quantum world. It allows systems to adapt, to evolve, and to form complex patterns that would not be possible if everything were fixed from the beginning. Superposition also invites a deeper philosophical reflection. In everyday life, we often think in terms of clear categories. Something is true or false, something exists or does not exist. But quantum physics suggests that reality may not always follow such strict divisions. There may be moments where multiple truths coexist, where outcomes are not yet resolved, where possibilities remain gently present. This idea can feel unfamiliar, but it can also be peaceful. It reminds us that not everything needs to be decided immediately. There is value in allowing possibilities to remain open, in letting things unfold over time. Superposition also connects to the idea of probability. Each possible state has a certain likelihood, a weight that describes how strongly it contributes to the whole. These weights combine to form the overall behavior of the system, guiding what we are most likely to observe. But until observation occurs, all these possibilities remain part of the system. They are not hidden or separate. They are present, quietly shaping the structure of reality. Imagine a soft cloud in the sky. It does not have a sharp boundary. It spreads gently, its shape defined by subtle variations. In a similar way, a quantum system in superposition is not confined to a single state. It exists as a spread of possibilities, forming a kind of probability cloud. As time passes, this cloud evolves. It shifts, expands, and interacts with its surroundings. And when the moment of interaction comes, one part of the cloud becomes definite, while the rest quietly recede. This process is not chaotic. It is guided by precise mathematical relationships, even if those relationships are not always visible to us. Superposition is also essential in modern technologies, especially in the development of quantum computing. In such systems, units of information can exist in multiple states at once, allowing many calculations to be explored simultaneously. This ability arises directly from superposition, from the capacity to hold multiple possibilities together. But beyond its applications, superposition offers something more reflective. It invites us to see reality as layered, as something that unfolds gradually rather than appearing fully formed. It suggests that beneath every clear outcome, there was once a range of possibilities, quietly interacting and shaping what would come to be. Take a moment to rest with this idea. Before something becomes definite, it exists as potential. Before a choice is made, multiple paths are present. Before clarity, there is openness. Superposition is this openness, expressed at the deepest level of reality. It is not confusion. It is not disorder. It is a calm and structured coexistence of possibilities. The observer effect is one of the most subtle and quietly unsettling ideas in quantum physics. At first, observation seems simple. To observe something is just to look at it, to notice it without changing it. In everyday life, we assume that things exist in a fixed way, whether we pay attention to them or not. But as we look closer, this assumption begins to soften. In the quantum world, observation is not passive. To observe something is to interact with it. And this interaction, however gentle, can influence what is being observed. The act of measurement becomes part of the system itself. Take a moment to imagine trying to see something very small. To observe it, you might shine light upon it. But light is not just illumination. It carries energy. When it touches a particle, it can gently shift its position or alter its motion. Even the smallest interaction can have an effect. This is the essence of the observer effect. It is not simply that we disturb what we measure. It is that measurement and system cannot be fully separated. They are connected, woven together in a quiet and unavoidable way. At first, this may seem like a limitation, a barrier to perfect knowledge. But as we look deeper, it begins to feel like a fundamental feature of reality. Consider again the experiment with two narrow openings. When particles such as electrons pass through without being observed, they form a pattern that suggests wave-like behavior. A gentle interference pattern emerges, as if each particle explores many paths at once. But when we try to observe which opening the particle passes through, something changes. The pattern shifts. The wave-like behavior fades, and a more particle-like pattern appears. It is as if the act of observation guides the system into a more definite state. Take a moment to reflect on this. Before observation, there is openness. After observation, there is definition. The possibilities that once overlapped begin to settle into a single outcome. This does not mean that the observer creates reality in a direct or intentional way. It means that interaction shapes what becomes visible. The system responds to being measured, gently adjusting its behavior. This idea invites a deeper way of thinking. In everyday life, we often imagine ourselves as separate from what we observe. We look at the world as if from a distance, assuming that our presence does not matter. But the observer effect suggests that at a fundamental level, separation is not absolute. There is always some connection, some exchange, however small. Imagine touching the surface of water. Even the lightest touch creates ripples. The water responds, shifting in response to contact. In the same way, quantum systems respond to observation, not violently but gently, in subtle ways that shape outcomes. The observer effect also connects closely to the idea of superposition. Before measurement, a system can exist in multiple states at once. After measurement, it appears in a single state. The act of observing seems to guide this transition, moving from possibility to clarity. But this transition is not fully understood. It remains one of the most open questions in quantum physics. How exactly does observation lead to a definite outcome? What defines a measurement? Where does possibility end and reality begin? These questions do not have simple answers. Instead, they invite quiet reflection. The observer effect also reminds us of the limits of knowledge. We cannot step completely outside the system to observe it without influence. We are always part of the process, participants rather than distant watchers. This can feel unfamiliar, but it also carries a certain calmness. It suggests that reality is not something entirely separate from experience. It is something that unfolds through interaction, through connection, through presence. Take a moment to imagine a world where observation and existence are gently intertwined, where seeing is not just receiving information, but participating in the unfolding of events, where awareness itself plays a role, however small, in shaping what becomes real. This idea does not mean that thoughts alone control reality. Rather, it suggests that physical interactions, including those involved in measurement, are part of the system. The boundary between observer and observed becomes softer, less rigid. The observer effect also appears in many practical situations. In scientific experiments, great care is taken to minimize disturbance. In sensitive measurements, even small interactions can influence results. This awareness has led to careful methods and techniques designed to observe systems as gently as possible. Yet even with the greatest care, complete separation is not possible. There is always some level of interaction, some quiet exchange between observer and system. This understanding has shaped the way modern physics approaches knowledge. Instead of seeking absolute certainty, it works with probabilities and relationships. It accepts that observation is part of the process, not something that can be removed. The observer effect also has a philosophical side. It invites us to reconsider the nature of reality itself. Is reality fully defined before it is observed, or does it remain open in some way, becoming more definite through interaction? Different interpretations of quantum physics offer different perspectives, but all acknowledge the importance of observation. Take a moment to reflect on your own experience. When you focus on something, it becomes clearer. Details emerge that were not noticed before. Your attention shapes what stands out, what becomes meaningful. In a gentle way, this mirrors the observer effect. Not in a literal sense, but in the idea that attention and interaction bring clarity. The observer effect teaches us that reality is not entirely distant or fixed. It is responsive, subtle, and interconnected. Quantum entanglement is one of the most quiet and mysterious ideas in quantum physics. At first, it seems almost impossible. Two particles become connected in such a way that the state of one is linked to the state of the other, no matter how far apart they are. In everyday life, distance usually separates things. If two objects are far apart, what happens to one does not immediately affect the other. This feels natural and expected. But in the quantum world, this sense of separation begins to soften. When two particles become entangled, they no longer behave as completely independent objects. Instead, they form a single system, even when they are separated by great distances. Take a moment to imagine this. Two particles begin close together, interacting in a gentle and precise way. During this interaction, their properties become linked. Afterward, they move apart, perhaps drifting across vast distances. Yet something of their connection remains. If we measure one particle, we instantly know something about the other, not because information travels between them in the usual sense, but because their states were never truly separate to begin with. They are part of one shared description, one quiet structure that extends across space. This idea can feel unsettling at first. It challenges the way we think about distance and independence. There is also a calmness in it, a sense that the universe may be more connected than it appears. To understand this more gently, imagine a pair of gloves. If you place one glove in one box and the other glove in another box, and then send the boxes far apart, opening one box immediately tells you what is in the other. If you find a left glove, the other must be a right glove. But quantum entanglement is more subtle than this. Before measurement, the particles are not simply waiting with fixed properties. Instead, they exist in a shared state of possibility. Their properties are not fully defined until one is measured. When that measurement occurs, the system settles into a definite pair of outcomes, consistent with their connection. Take a moment to reflect on this. Before observation, there is a shared openness. After observation, there is a coordinated result. The two particles behave as if they are part of a single whole, even across distance. This does not mean that one particle sends a signal to the other faster than light. Rather, it means that the system as a whole contains the correlation from the beginning. The connection is built into the structure of their shared state. This idea was once described as spooky action at a distance, a phrase that reflects how unusual it feels, but over time, it has become a well-tested and carefully studied part of quantum physics. Experiments have shown again and again that entangled particles display correlations that cannot be explained by simple hidden properties assigned in advance. Their connection goes beyond classical intuition. Take a moment to imagine two distant points connected not by a visible line, but by a quiet relationship. No signal passes between them in the moment of measurement. Instead, the outcome reflects a deeper level of unity, something that is not easily seen but is consistently present. This invites a different way of thinking about space. In classical physics, space separates objects. In quantum physics, certain relationships can extend across space, linking systems in ways that do not depend on distance in the usual sense. This does not remove the importance of space, but it adds another layer beneath it, a layer where connection is not always limited by distance. Quantum entanglement also plays an important role in modern technology. It is used in quantum communication and quantum computing, where these deep connections allow information to be processed and shared in new ways. These applications rely on the precise and delicate nature of entangled states, but beyond its practical uses, entanglement offers something more reflective. It suggests that the universe may not be made entirely of separate pieces. Instead, there may be levels at which everything is part of a larger, interconnected structure. Take a moment to consider this gently. Two particles, once connected, continue to share a relationship, even when separated. Their behavior reflects a unity that is not immediately visible. In a quiet way, this mirrors patterns we sometimes notice in life. Events that seem separate may share underlying connections. Outcomes that appear independent may be linked in ways we do not fully see. This does not mean that everything is directly connected in a simple or obvious sense, but it suggests that connection can exist in subtle forms beneath the surface of what we observe. Quantum entanglement also raises deep questions about reality. Are particles truly independent entities, or are they expressions of a deeper whole? Is separation an absolute feature of the universe, or does it emerge from something more unified? These questions do not have simple answers. Instead, they invite quiet reflection. Take a moment to imagine the universe as a gentle web of relationships, not a rigid structure, but a soft and interconnected pattern, where parts influence one another in ways that are not always visible. In this view, entanglement is not an anomaly. It is a glimpse into a deeper level of order, a level where connection is fundamental, and where separation is not always complete. The Schrödinger Paradox is one of the most well-known and quietly puzzling ideas in quantum physics. At first, it may seem unusual, even slightly strange, but as we look closer, it becomes a gentle way of exploring a deeper question about reality itself. The paradox was introduced as a thought experiment. A thought experiment is not something meant to be physically carried out, but something imagined, carefully constructed to reveal hidden ideas. In this case, it was designed to show how quantum principles might appear when applied to everyday objects. Take a moment to imagine a closed box. Inside the box, there is a small system. Within this system is a particle that can exist in a superposition, meaning it can be in multiple states at once. This particle is connected to a mechanism, a simple device that depends on the state of the particle. If the particle is in one state, the mechanism remains inactive. If the particle is in another state, the mechanism is triggered. Now imagine that this mechanism is linked to something more familiar, something larger and easier to picture. Inside the box, there is also a cat. The state of the cat depends on the mechanism. If the mechanism is triggered, one outcome occurs. If it is not triggered, a different outcome occurs. Because the particle is in a superposition, The system as a whole becomes linked to this uncertainty. The cat, in this thought experiment, is described as being in a superposition as well, not simply in one state or the other, but in a blend of possibilities. At first, this idea feels difficult to accept. In everyday life, we do not see objects existing in multiple states at once. A cat is either in one condition or another. The idea that it could be both at the same time seems to challenge our basic understanding, but this is the purpose of the paradox. It invites us to question how quantum ideas scale from the smallest particles to the larger world we experience. Take a moment to reflect on this. Inside the box, before it is opened, the system is described by a range of possibilities. The particle is not fixed in one state, and because of its connection to the mechanism, the entire system reflects this uncertainty. Only when the box is opened, when observation occurs, does the system appear to settle into a single outcome. This raises a quiet and important question. When does the transition from possibility to reality actually happen? Is it at the level of the particle? Is it when the mechanism is triggered, or is it only when an observer looks inside the box? These questions do not have simple answers. Instead, they reveal the subtle nature of measurement and observation in quantum physics. The Schrödinger Paradox highlights the difference between the quantum world and the classical world. At very small scales, systems can exist in superpositions. At larger scales, we observe definite outcomes. Somewhere between these two levels, something changes. Take a moment to imagine a gentle fading. At the smallest level, there is openness, a blending of possibilities. As systems grow larger and interact with their surroundings, this openness begins to settle. The many possibilities reduce, leaving behind a single stable outcome. This process is often connected to what is called decoherence, a gradual loss of quantum behavior as systems interact with the environment. But even with this explanation, the deeper question remains: what is the true nature of the superposition? Is it a physical reality where multiple outcomes truly coexist, or is it a description of our knowledge, a way of expressing uncertainty about the system? Different interpretations of quantum physics offer different perspectives. Some suggest that all possible outcomes exist in parallel, branching into separate realities. Others suggest that the act of observation plays a key role in selecting a single outcome. The Schrödinger paradox does not resolve these questions. Instead, it gently presents them, inviting reflection. Take a moment to imagine the closed box once more. Inside, there is a quiet stillness, a system that holds multiple possibilities at once, not yet resolved, not yet defined. From the outside, we do not know the outcome. From the inside, the system follows the rules of quantum physics, evolving as a superposition. Only when the box is opened does clarity emerge. This moment of opening can be seen as a transition, a gentle shift from uncertainty to certainty. But even this description raises questions. Does the act of opening the box create the outcome, or does it simply reveal what was already there? The paradox leaves this open. It does not force an answer. Instead, it encourages us to sit with the uncertainty, to explore the idea without rushing to resolve it. There is a calmness in this approach. It allows space for complexity, for multiple interpretations, for ideas that do not fit neatly into simple categories. The Schrödinger paradox also reminds us of the limits of intuition. Our everyday experiences are shaped by the classical world, where objects behave in predictable ways. But the quantum world follows different rules that do not always align with our expectations. This does not mean that the quantum world is chaotic. It is structured, precise, and governed by mathematical relationships. But its structure is subtle, often hidden beneath layers of abstraction. Take a moment to reflect on this contrast: a world where things are clearly defined, and a world where possibilities overlap, where outcomes are not fixed until they are observed. The Schrödinger paradox sits between these two worlds. It acts as a bridge, a way of bringing quantum ideas into a form we can imagine, even if it feels unusual. Quantum tunneling is one of the most quiet and surprising ideas in quantum physics. At first, it seems almost impossible. In everyday experience, if something encounters a barrier, it must either go over it or stop. A ball cannot pass through a solid wall. It lacks the energy to cross, so it remains on one side. But in the quantum world, this simple rule begins to soften. Quantum tunneling describes a process where a particle can pass through a barrier, even when it does not have enough energy to cross it in the usual sense. It does not climb over the barrier. It does not break through it. Instead, it appears on the other side, as if it has quietly moved through. Take a moment to imagine this. A small particle approaches a barrier, something like a hill. In classical thinking, if the particle does not have enough energy, it cannot reach the top. It will roll back, unable to continue. But in the quantum world, the particle is not just a single point. It behaves like a wave, gently spread out across space. This wave does not stop sharply at the barrier. Instead, it extends slightly into it, fading gradually rather than ending abruptly. Within this extension, there is a small but real possibility. A part of the wave can reach beyond the barrier, and because the particle is described by this wave, there is a chance that it will be found on the other side. This is quantum tunneling. It is not a forceful crossing. It is a quiet emergence. The particle does not travel through the barrier in a visible path. Instead, its probability spreads into the barrier, and a small portion appears beyond it. Take a moment to reflect on this image. A soft wave approaching a boundary, gently fading into it, with a faint presence on the other side. Over time, this faint presence can become an outcome, a realization of possibility. This idea may feel unfamiliar, but it carries a certain calmness. It suggests that boundaries are not always absolute. Even when something seems impossible, there may be a subtle path, a quiet way through. Quantum tunneling depends on several factors. The height and width of the barrier influence the likelihood of tunneling. A thinner barrier allows more of the wave to extend through. A lower barrier increases the probability that the particle will appear on the other side. But even with a strong barrier, the probability is not always zero. There is often a small chance, a gentle possibility. This introduces a different way of thinking about limits. In classical physics, limits are firm and final. In quantum physics, limits can become soft, allowing for rare but meaningful events. Take a moment to imagine a fog drifting toward a wall. The fog does not stop sharply. It touches the surface, spreads slightly, and in some cases, a faint trace may appear beyond. The wall remains, but its boundary is not perfectly rigid for the fog. In a similar way, quantum particles interact with barriers in a gradual and subtle manner. Quantum tunneling is not just a theoretical idea. It plays an important role in the natural world. For example, it is essential in the processes that power stars. In the core of a star, particles must come close enough to interact, even when they do not have enough energy to overcome their mutual repulsion. Tunneling allows these interactions to occur, enabling the reactions that produce light and heat. In this way, a quiet quantum effect contributes to the brightness of the night sky. Quantum tunneling is also used in modern technology. Devices such as scanning tunneling microscopes rely on this effect to observe surfaces at extremely small scales. By measuring how particles tunnel across tiny gaps, these instruments can reveal structures that would otherwise remain hidden. Once again, something subtle becomes useful, transforming quiet probability into practical knowledge. But beyond its applications, quantum tunneling invites a deeper reflection. It suggests that reality is not always confined by rigid boundaries. Even when paths seem blocked, there may be hidden possibilities, small chances that allow movement beyond what appears to be a limit. This does not mean that all barriers can be crossed easily. The probabilities can be very small. The conditions must be just right, but the presence of possibility itself changes how we think about what is allowed. Take a moment to consider this gently. A system approaching a limit, not stopping completely, but extending slightly beyond. A faint continuation, a quiet persistence. Quantum tunneling also connects to the broader idea of uncertainty. Because particles are described by waves, their position is not perfectly defined. This spread allows them to interact with regions beyond what would be expected in a classical sense. Once again, we see how the softness of quantum behavior leads to unexpected outcomes. The world at this scale is not made of sharp edges and fixed paths. It is made of gradients, probabilities, and gentle transitions. Imagine a landscape not with solid walls, but with soft hills and fading boundaries. Movement is not restricted to clear paths. Instead, there are subtle ways to pass through, guided by the shape of the underlying wave. This image captures something of the quiet nature of tunneling. It is not dramatic. It is not forceful. It is a calm and continuous unfolding of possibility. Vacuum fluctuations are one of the most subtle and quietly fascinating ideas in quantum physics. At first, the concept of a vacuum seems simple. It is often described as empty space, a region with nothing in it, no matter, no particles, no activity, just stillness. But as we look closer, this idea begins to soften. In the quantum world, a vacuum is not truly empty. Even in the absence of particles, there remains a gentle background activity, a constant and subtle motion that never fully disappears. This activity is known as vacuum fluctuations. Take a moment to imagine complete emptiness, a silent space, still and unchanging. Now slowly allow that image to shift. Instead of perfect stillness, imagine a faint flickering, something so small and brief that it almost escapes notice, tiny appearances and disappearances, like soft sparks that emerge and fade. This is closer to what a quantum vacuum is like. Within this space, pairs of particles can briefly appear and then disappear again. They do not remain long enough to be directly observed in the usual sense, but their presence can be detected through their effects. This may seem surprising. How can something come from nothing, even for a moment? The answer lies in the uncertainty principle, which we explored earlier. There is a relationship between energy and time. For very short periods, small amounts of energy can appear, as long as they vanish again quickly enough. This allows for temporary fluctuations, brief shifts in energy that give rise to these particle pairs. Take a moment to reflect on this. Even in what we call empty space, there is motion, not large or dramatic, but gentle and constant, a quiet background activity that never fully rests. These fluctuations are not random in a chaotic sense. They follow precise patterns described by quantum theory. The appearances and disappearances are governed by underlying rules, even if they seem unpredictable on the surface. This creates a world where stillness is not absolute. Even the calmer space contains a subtle energy, a quiet vibration beneath the surface. Imagine a calm lake. From a distance, it appears completely still. But if you look closely, there are always small ripples, tiny movements caused by faint currents or gentle breezes. The surface is never perfectly motionless. In a similar way, the quantum vacuum is never completely empty. It is filled with small fluctuations, tiny variations that give it a kind of texture, even though it appears smooth at first glance. Vacuum fluctuations also have measurable effects. One example is the Casimir effect, where two closely spaced surfaces experience a small force due to changes in these fluctuations between them. This effect has been observed and studied, showing that these subtle quantum processes have real consequences. Another example is their role in the structure of the universe. Some theories suggest that vacuum fluctuations in the early universe contributed to the formation of galaxies and large-scale structures. Tiny variations in energy may have been amplified over time, shaping the patterns we see today. In this way, something very small and fleeting may have influenced something vast and enduring. Take a moment to consider this connection. From brief and subtle fluctuations, entire structures may emerge. From quiet variations, patterns can grow and expand. Vacuum fluctuations also remind us of the limits of the idea of nothingness. We often think of nothing as the absence of everything, but in quantum physics, even nothing has properties. It is not a simple void, but a state with structure and activity. This challenges our intuition in a gentle way. It suggests that emptiness itself is not empty, that beneath what appears to be nothing, there is something quietly present. This idea can feel calming. It replaces the idea of complete absence with one of subtle presence, a background of gentle motion that supports the existence of particles and fields. Take a moment to imagine space not as an empty container, but as a soft fabric. This fabric is never perfectly still. It shifts slightly, creating small ripples and patterns that come and go. These ripples are not permanent, but they are part of the nature of the fabric itself. In this image, vacuum fluctuations are like tiny waves on that fabric. They do not dominate the space, but they are always there, quietly shaping its behavior. Vacuum fluctuations also connect to the concept of quantum fields. Each type of particle is associated with a field that exists throughout space. Even when no particles are present, the field remains. It can still fluctuate, producing these temporary effects, so what we call empty space is actually filled with fields, each gently fluctuating. This adds another layer of depth. Space is not just a background, it is active, dynamic, and full of subtle processes. Take a moment to rest with this idea. A space that seems empty yet is quietly alive with motion. A stillness that contains gentle change. A simplicity that hides complexity. Vacuum fluctuations also invite philosophical reflection. They suggest that absence and presence are not always clearly separated. That even in emptiness, there is a trace of existence. That nothingness may not be absolute, but instead a kind of quiet potential. This perspective can shift how we think about reality. Instead of viewing the universe as made of isolated objects in empty space, we can see it as a continuous system, where even the spaces between objects are active and meaningful. Zero-point energy is one of the most quiet and deeply subtle ideas in quantum physics. At first it may seem simple. When something loses all its energy, we expect it to come to rest. A moving object slows down and eventually it stops. Stillness feels like the natural end of motion. But as we look closer, this expectation begins to soften. In the quantum world, complete stillness does not truly exist. Even at the lowest possible energy level, a system still contains a small amount of motion. This remaining energy is called zero-point energy. Take a moment to imagine cooling something down. As the temperature drops, motion decreases. Particles move more slowly. Vibrations become softer. Everything begins to quiet down. It may seem that if we continue this process, we could reach a point where all motion disappears completely. But quantum physics suggests otherwise. There is always a minimum level that cannot be removed. Even at what we call absolute zero temperature, a system still has energy. It still moves gently and quietly, never fully at rest. This idea is closely connected to the uncertainty principle. If a particle were completely at rest, with no motion at all, its position and momentum would both be perfectly defined. But the uncertainty principle tells us that this is not possible. There must always be some spread, some softness in these properties. As a result, a particle cannot be perfectly still. It must retain a small amount of motion, a quiet vibration that remains even in the lowest energy state. Take a moment to reflect on this. Stillness is not absolute. Even in the calmest state, there is movement. Even in the quietest moment, there is a subtle activity beneath the surface. This can be imagined as a gentle trembling, not a large or noticeable motion, but a faint and continuous presence like a soft hum that never fully fades. Zero-point energy appears in many quantum systems. For example, consider a simple system like a particle confined in a small region. In classical thinking, the particle could come to rest at the lowest point with zero energy, but in quantum physics, the particle always retains some motion, some energy that cannot be removed. This energy is not added from outside. It is part of the system itself. It arises from the fundamental nature of quantum behavior, from the balance between position and motion, from the structure of uncertainty. Take a moment to imagine a small space, like a tiny box. Inside, a particle moves gently, never fully stopping. It cannot settle into a single fixed point. Instead, it continues to shift, its motion guided by the constraints of the system. This motion is not chaotic. It is structured and consistent, following precise patterns described by quantum theory. Zero-point energy is also connected to the idea of quantum fields. Even when no particles are present, the fields that fill space still exist, and these fields are never completely still. They fluctuate, gently vibrating, contributing to the energy of the vacuum. This means that even empty space contains zero-point energy. A quiet background presence, always there, always active at a subtle level. Take a moment to imagine space itself as something that can never fully rest, a fabric that always carries a slight vibration, a soft movement that remains even in complete darkness and stillness. This idea can feel calming. It suggests that rest is not the absence of motion, but a balance of motion at its most gentle level, a state where activity continues but in a quiet and stable form. Zero-point energy also has measurable effects. It contributes to phenomena such as vacuum fluctuations and subtle forces observed in experiments. These effects show that even the lowest energy states have real physical consequences. Once again, something that seems abstract becomes tangible, a quiet energy, always present, influencing the behavior of systems in ways that can be observed and studied. But beyond its scientific importance, zero-point energy invites a deeper reflection. It challenges the idea of complete emptiness and complete stillness. It suggests that there is always something beneath the surface, a small but persistent presence that cannot be removed. Take a moment to consider this gently. Even in the quietest place there is motion. Even in the simplest system there is energy. Even in stillness, there is life at a subtle level. This perspective can shift how we think about rest. Rest is not absolute silence. It is a soft balance, a steady state where movement continues in a calm and controlled way. Zero-point energy also connects to the broader theme of quantum physics, a theme of softness, of limits, of gentle constraints that shape reality. We cannot remove all motion. We cannot define everything precisely. We cannot reduce systems to perfect stillness. Instead, we find a world that is always slightly in motion, always carrying a trace of uncertainty and possibility. Imagine a quiet room. At first, it seems completely still, but if you listen closely, there is always a faint sound, a subtle presence that never fully disappears. In the same way, zero-point energy is like a background hum, always present, always part of the system. Quantum fields are one of the most gentle and foundational ideas in modern physics. At first, we often imagine the world as being made of small solid particles, tiny pieces of matter moving through empty space. This picture feels simple and intuitive. But as we look closer, this image begins to soften. In quantum physics, particles are not the most fundamental things. Instead, they arise from something deeper, something more continuous. These underlying structures are called quantum fields. A field can be thought of as something that exists everywhere in space. It is not located in just one place. It stretches across all of reality, present at every point, even in regions that appear empty. Take a moment to imagine a calm ocean. The ocean extends in all directions, forming a continuous surface. Now imagine small waves forming on this surface. Each wave rises, moves, and then fades back into the water. In a similar way, quantum fields fill all of space, and what we call particles are like small excitations or disturbances in these fields. A particle is not a tiny solid object in the traditional sense. It is more like a localized vibration in a field, a small ripple that appears and behaves as a distinct entity for a time. This idea changes how we think about matter. Instead of separate objects moving through empty space, we have a continuous background of fields, with patterns of vibration appearing within them. Take a moment to reflect on this. Not isolated points, but continuous presence. Not solid objects, but gentle patterns of motion. Each type of particle is associated with its own field. There is a field for electrons, a field for light, and many others. These fields overlap, existing together in the same space, interacting in subtle ways. Even when no particles are present, the fields remain. They do not disappear. They continue to exist, quietly and constantly, forming the foundation of reality. This connects to what we explored earlier with vacuum fluctuations and zero-point energy. Empty space is not truly empty because these fields are always there, gently fluctuating, never completely still. Take a moment to imagine space not as a void, but as a soft fabric woven from many overlapping layers. Each layer represents a field extending everywhere, interacting with the others. Within this fabric, small vibrations appear, forming the particles we observe. This image can feel calming. It suggests continuity rather than separation, a smooth and connected structure rather than a collection of isolated pieces. Quantum fields also help explain how particles are created and destroyed. In classical thinking, objects are permanent unless acted upon. But in quantum physics, particles can appear and disappear as excitations in fields. When the vibration forms, we observe a particle. When it fades, the particle is no longer present. The field itself remains unchanged in its existence, even as its excitations come and go. Take a moment to imagine a still surface of water again. Waves rise and fall, but the water itself remains. The waves are temporary, but the ocean is continuous. In the same way, particles are temporary expressions of deeper fields. This perspective can shift how we think about existence. Instead of focusing only on individual objects, we begin to see the underlying patterns that give rise to them. We notice the continuity beneath the change. Quantum fields also play a central role in how forces are understood. Interactions between particles are described as interactions between fields. These interactions are mediated by excitations, often called force carriers, which move between regions of the field. But even this movement is part of the same continuous structure. There is no need for empty space to carry something from one place to another. The fields themselves provide the connection. Take a moment to consider this gently, a universe where everything is connected through underlying fields, where interactions are not separate events, but expressions of a shared structure. This idea reduces the sense of separation. It suggests that what we perceive as distinct objects are actually patterns within a larger whole. Quantum fields also bring a sense of stability. Because fields exist everywhere, they provide a consistent foundation. The behavior of particles follows from the properties of these fields, leading to regular patterns and predictable relationships. Even though quantum behavior can seem uncertain, the fields themselves follow precise mathematical rules. There is order beneath the complexity. Take a moment to reflect on this balance. A world that appears unpredictable at small scales, it is guided by deep and consistent structures. A world where change and stability coexist. Quantum fields also invite philosophical reflection. They suggest that the idea of a separate object may be less fundamental than the idea of a pattern within a whole. A particle is not something entirely independent. It is a localized expression of a field that exists everywhere. This can be seen as a gentle shift in perspective, from objects to patterns, from separation to continuity, from fixed identity to dynamic expression. Imagine a piece of music. The notes are not separate from the melody. They rise from it, exist within it, and fade back into it. The melody continues, even as individual notes come and go. In a similar way, quantum fields provide the background melody of reality, while particles are like notes that briefly emerge. Particle illusions are one of the most quiet and thought-provoking ideas in quantum physics. At first, the idea of a particle seems simple. A particle is often imagined as a tiny, solid object, like a small grain of matter, something with a clear position, a defined shape, and a stable existence. But as we look closer, this image begins to soften. In the quantum world, particles are not quite what they seem. They do not exist as small, solid points in the way we might expect. Instead, they behave more like patterns of probability, gently spread out and only becoming definite when observed. Take a moment to imagine a small point in space. Now slowly allow that point to blur. Instead of a sharp location, imagine a soft cloud, a region where the particle is likely to be found, but not confined to a single exact position. This cloud is often described as a probability distribution. It does not tell us where the particle is with certainty. It tells us where the particle might appear when we observe it. This shift from certainty to probability is at the heart of particle illusions. The particle appears as a point when measured, but before that, it exists as a spread of possibilities. Take a moment to reflect on this. What we observe is not the full story. It is a single outcome, drawn from a wider range of potential states. In this sense, the idea of a particle as a fixed object is an approximation, a simplified picture that works in everyday situations but does not fully capture the deeper reality. This can feel surprising. We are used to thinking of objects as having definite properties at all times. But quantum physics suggests that at very small scales, properties such as position are not always fixed. They are described by a wave function, which is a mathematical way of representing the spread of possibilities. When we observe the particle, this spread appears to collapse into a single point, but before that moment, the particle is not localized in the usual sense. Take a moment to imagine watching a distant cloud. From far away, it appears soft and undefined, but if you could focus on a single droplet within it, you would see something more precise. In a similar way, a quantum particle appears as a definite point when measured, but its underlying nature is more like a cloud. This is why the idea of a particle can be seen as an illusion. Not an illusion in the sense of being unreal, but an illusion in the sense of being incomplete. It is a simplified image of something more complex and subtle. Particle illusions also connect closely to wave duality. As we explored earlier, particles can behave like waves. This wave-like behavior spreads out over space, creating interference patterns and probability distributions. When we detect a particle, we see a single point, but this point emerges from a wave-like process. Take a moment to consider this gently. A wave spreads across space, carrying many possibilities. Then, in a moment of observation, one outcome appears, a single point that we call a particle. This point is real, but it does not represent the full nature of the system. It is one expression of a deeper structure. Particle illusions also appear in how we think about motion. In classical physics, a particle moves along a clear path, a trajectory that can be traced over time. But in quantum physics, this idea becomes less certain. Instead of a single path, there is a range of possible paths, each contributing to the overall behavior. The particle does not follow one definite route. It explores many possibilities, and what we observe is the result of this combination. This creates a different picture of motion. Not a single line, but a soft collection of paths, overlapping and interacting. Take a moment to imagine walking through a field. Instead of choosing one path, imagine that all possible paths exist at once, gently overlapping. The final position emerges from this blend, not from a single predetermined route. This is closer to how quantum systems behave. Particle illusions also remind us of the limits of perception. Our senses and everyday experiences are shaped by larger scales, where objects appear solid and well-defined. But at smaller scales, these familiar ideas begin to break down. What seems solid is mostly empty space. What seems fixed is often dynamic. What seems simple is layered with complexity. This does not make reality less real. It makes it more subtle. Take a moment to reflect on this shift. From solid to soft, from fixed to fluid, from certainty to probability. Particle illusions also connect to the idea of measurement. When we measure a particle, we interact with it, and this interaction brings about a definite outcome. The particle appears at a specific location with specific properties, but this outcome depends on the measurement. Different types of measurements can reveal different aspects of the system. This suggests that what we observe is not just a property of the particle alone, but a result of the interaction between the system and the measurement. Again, the idea of a particle as a simple, independent object becomes less complete. It is part of a larger process, a relationship between possibilities and observation. Take a moment to imagine a shadow on a wall. The shadow has a clear shape, but it depends on the light and the object creating it. Change the light, and the shadow changes. In a similar way, the properties we observe in a particle depend on how we look at it. The particle is not just a fixed thing, it is part of an interaction, part of a process. Particle illusions also have practical importance. They are essential in understanding the behavior of electrons and atoms, the structure of materials, and the functioning of modern technologies. By recognizing that particles are not simple points, scientists can better describe and predict their behavior. But beyond their practical use, particle illusions offer a deeper reflection. They remind us that reality is not always what it appears to be, that what we see is often a simplified version of something more complex, that beneath clear images there may be layers of subtle structure. Time uncertainty is one of the most subtle and quietly unsettling ideas in quantum physics. At first, we think of time as a steady flow, a continuous river that moves forward at a constant pace. Clocks tick, days pass, and we measure intervals with precision. This sense of regularity feels natural and absolute. But as we look closer, time begins to reveal a gentler, more flexible nature. In the quantum world, time is not always perfectly precise. It is intimately connected to energy, and the uncertainty principle tells us that the more precisely we measure one, the less precisely we can know the other. Specifically, there is a relationship between the uncertainty of energy and the uncertainty of time. When a system has a brief duration, there can be a small fluctuation in energy. When we try to fix energy precisely, the corresponding moment in time becomes less certain. Take a moment to imagine a soft pulse, a brief vibration lasting only for a short moment. Within that fleeting instant, the energy associated with the pulse can vary slightly. It is not fixed. It is gentle, flexible, and quietly uncertain. This is the essence of time uncertainty. It is not chaos. It is a balance, a subtle interplay between how precisely we can define energy and how precisely we can define time. One constrains the other, softly and continuously. Time uncertainty is deeply connected to many quantum processes. For example, consider the creation and disappearance of particles in the vacuum. In extremely brief intervals, particle pairs can appear and vanish, their energy allowed to fluctuate slightly according to the limits imposed by time uncertainty. These fleeting events would be impossible if time and energy were perfectly fixed. Take a moment to reflect on this. Even in what we perceive as emptiness, there is motion. Even in the smallest slices of time, there is a gentle flexibility. The flow of time is not absolute, but carries within it a soft margin of possibility. This uncertainty also affects how we understand decay processes. Unstable particles do not decay at perfectly predictable moments. Instead, there is a probabilistic distribution of times at which the decay can occur. The energy involved and the timing are subtly linked by the same quantum principle, giving rise to natural variation without violating any fundamental laws. Imagine a soft candle flickering in a quiet room. You cannot predict the exact instant each small change of flame occurs, but the overall process is smooth, governed by gentle patterns. Time uncertainty is similar. It is the natural ebb and flow of possibilities at the smallest scales. Time uncertainty also suggests that our usual way of slicing reality into precise moments may not fully capture the nature of quantum events. Instead of discrete, absolute ticks, we can think of time as a soft continuum, where small fluctuations are always present, quietly shaping outcomes. Consider again a brief interval of time. Within that interval, multiple possible energy levels coexist as possibilities. Only when the system interacts with something else, when a measurement occurs, does a specific outcome manifest. Until then, time and energy remain softly intertwined, a gentle dance of probability. This interplay has profound implications for how we understand the evolution of quantum systems. Events are not strictly fixed. Outcomes emerge in connection with both their temporal context and the underlying energy fluctuations. There is an inherent fluidity, a softness to the unfolding of reality, even at its most precise scales. Take a moment to imagine a gentle ripple across a calm pond. Each ripple represents a moment in time, but the water is never perfectly still. Tiny variations occur continuously, subtle shifts that are always present. Time uncertainty operates in a similar way. The flow of moments is never perfectly uniform, and each interval carries the quiet possibility of variation. Time uncertainty also plays a role in some of the most fundamental phenomena in quantum physics, including tunneling, vacuum fluctuations, and particle creation. It ensures that even in empty space or seemingly still moments, there is always a subtle dynamism present. Nothing is ever completely frozen. Nothing is ever fully rigid. This realization invites a reflective perspective. Time, like many aspects of quantum reality, is not simply a background that moves uniformly and independently of everything else. It is interwoven with the energies and possibilities of the systems it measures, quietly shaping what can and cannot happen. Take a moment to imagine your own experience of time. Even when moments feel steady and measured, there is a subtle rhythm beneath perception, a natural variability in how events unfold, invisible yet real. This quiet rhythm mirrors the principles of time uncertainty, showing that uncertainty is not a flaw but a gentle feature of existence. Time uncertainty also softens the rigid boundaries we often impose on reality. Events are not isolated points, they are intervals filled with subtle fluctuations, gently influencing one another. Outcomes are not predetermined in absolute detail, but emerge from a continuum of possibilities that is constantly in motion. Consider a soft twilight fading into night. The moment of transition is not instantaneous, it stretches gently with light and shadow blending gradually. Time uncertainty behaves similarly. Intervals are not absolute points, but overlapping shades of possibility, softly interwoven with energy fluctuations. Quantum decoherence is one of the most subtle and quietly transformative concepts in quantum physics. At first, it may seem abstract, almost elusive. We are used to thinking of quantum systems as being isolated, capable of existing in multiple states at once, suspended in delicate superpositions. But in reality, very few systems are perfectly isolated. They interact gently with their surroundings, and it is in these interactions that decoherence emerges. Take a moment to imagine a small particle in a quiet space. In perfect isolation, it exists in a superposition, a combination of possibilities. It is simultaneously here and there, moving in multiple ways at once. Its state is delicate, fragile, and full of potential. Now slowly, allow the image to expand. The particle is no longer alone. It begins to interact with nearby particles, the surrounding environment, perhaps even a faint background field. Each interaction is gentle, subtle, but significant. Every contact, every tiny disturbance contributes to a gradual change. This is the essence of quantum decoherence. It is the process by which quantum systems lose their coherent superpositions, merging subtly with the environment in a way that makes the multiple possibilities appear to collapse into one outcome. Decoherence does not destroy the system, nor does it violate quantum principles. It simply entangles the system with its surroundings, spreading the superposition quietly across many degrees of freedom. Take a moment to reflect on this. Imagine a drop of ink in a still glass of water. At first, the drop is concentrated, distinct, and coherent. Slowly, over time, it spreads, diffuses, and blends with the water. Its identity remains, but the boundaries are softened. The drop no longer exists in isolation. It has merged subtly with its surroundings. Decoherence works in a similar way. Quantum states, once isolated and delicate, interact with their environment, causing the superposition to become entangled with countless external degrees of freedom. To an observer, this appears as though the system has selected a single outcome, though in reality the underlying quantum information is still present, dispersed quietly across the environment. This process helps explain a fundamental mystery. Why do quantum effects, so evident at tiny scales, rarely appear in the everyday world? Why do objects seem to follow classical rules, moving along definite paths, with properties we can measure directly? The answer lies in decoherence. As systems interact with their environment, superpositions are rapidly entangled and spread out. The delicate interference patterns that characterize quantum behavior are effectively washed out, leaving the appearance of classical outcomes. The world we perceive, with stable objects and predictable behavior, emerges naturally from these interactions. Take a moment to imagine a finely tuned mobile hanging in a quiet room. At first, each piece moves delicately, independent and precise. Introduce even a slight breeze from the environment, and the movement begins to blend subtly. Patterns shift, and the independence of each piece is lost. Decoherence is like that gentle breeze, softly distributing the quantum possibilities across the environment, transforming fragile superpositions into the familiar, classical patterns we observe. Decoherence also connects to the measurement problem in quantum physics. When we measure a quantum system, we rarely consider that the act of measurement is itself an interaction with a larger system, the measuring device, the observer, and even the surrounding air or electromagnetic fields. Each interaction entangles the system further, producing decoherence and the emergence of a definite outcome. In this sense, the collapse of the wave function is not a mystical event, but a natural consequence of entanglement with the environment. Take a moment to consider the philosophical side. Decoherence blurs the line between what is quantum and what is classical. It reminds us that our perception of discrete, stable objects is shaped by the gentle interplay between systems and their surroundings. It is not that the underlying quantum reality disappears, rather it is quietly spread across the vast environment, becoming less visible to direct observation. This idea is deeply reflective. It shows that observation and reality are intertwined, not in a dramatic or forceful way, but through the continuous, subtle process of interaction. Reality, at its deepest level, is not rigid, but a network of delicate connections, softly entangling, softly distributing possibilities across space and time. Imagine, for a moment, a single note played on a calm piano. The note begins sharply, distinct and clear. As it resonates, it interacts with the surrounding air, the wooden frame, and even the subtle vibrations in the floor. Gradually, the sound disperses, blending with the environment, softening and fading. Decoherence is like this gentle resonance. The purity of the quantum note spreads, merging with the surroundings, leaving a harmonious but more classical perception. Decoherence also plays a central role in modern technology. Quantum computers, for instance, rely on delicate superpositions to perform calculations that classical computers cannot. Decoherence is the enemy in this context. The slightest interaction with the environment can destroy coherence, collapsing superpositions and losing information. Engineers work tirelessly to isolate systems, maintain low temperatures, and shield them from noise, all to preserve the delicate balance needed for quantum computation. Yet even in these technical applications, there is a quiet lesson. Decoherence demonstrates the universality of quantum interactions. No system exists in absolute isolation. The world is fundamentally connected, each quantum state subtly influencing and being influenced by its surroundings. This interplay gives rise to the stability and regularity we observe at macroscopic scales, quietly shaping the reality we perceive. Take a moment to imagine sitting in a forest. Each leaf, each branch, each gust of wind subtly affects the others. The movements are gentle, interconnected, and continuous. Over time, a coherent pattern emerges from countless interactions. Decoherence works in a similar fashion, distributing quantum possibilities, allowing the classical world to emerge naturally and beautifully from the subtle quantum foundation. The many-worlds interpretation is one of the most quietly profound and mind-bending ideas in quantum physics. At first, it may seem almost impossible, even unsettling. We are accustomed to thinking of a single shared reality where events unfold along a definite timeline. One choice is made, one outcome occurs, and the world proceeds along that path. This is how our intuition guides us every day. But the many-worlds interpretation suggests a deeper, more expansive reality. Instead of a single outcome, every possible outcome of a quantum event actually occurs, each in its own branch of reality. The universe continuously splits into parallel versions, gently unfolding a vast tree of possibilities. Take a moment to imagine a quiet river. At first it flows in a single channel, steady and certain. Now imagine the river gradually dividing into multiple streams, each flowing alongside the others, sometimes reconnecting, sometimes diverging further. In a similar way, each quantum event creates a branching of realities, subtle and infinite, each as real as the others. This idea arises naturally from the mathematics of quantum physics. When a system is in a superposition, it exists in multiple states at once. Traditionally, we think that observation or measurement collapses this superposition into a single outcome. The many-worlds interpretation asks a different question. What if the superposition does not collapse at all? What if every possibility continues creating its own branch of reality? Take a moment to reflect on this gently. Each decision, each event is not singular. Each outcome unfolds somewhere quietly in a parallel thread of existence. The world we experience is only one branch, while countless others continue alongside it. This perspective transforms how we understand choice and possibility. Even something as simple as flipping a coin is not limited to two outcomes. In one branch, it lands heads. In another, it lands tails. Both outcomes occur, each quietly real in its own universe. Our perception of a single outcome is a reflection of the branch we inhabit, not a limitation of reality itself. The many worlds interpretation also provides a calm explanation for certain quantum paradoxes. For example, entangled particles exhibit correlations that seem instantaneous, defying ordinary expectations of space and time. In many worlds, these correlations are natural. Each measurement outcome exists in its own branch, and the appearance of spooky action at a distance is simply the alignment of outcomes across branches. No faster than light interaction is needed. Everything unfolds gently within the continuous branching of possibilities. Take a moment to imagine a vast tree of light. Each branch represents a universe, each leaf a moment of experience. The trunk of the tree is the shared history, the root, the origin of all events. As time progresses, the branches multiply, growing quietly and continuously, creating a vast network of parallel realities, all coexisting in a cosmic harmony. The implications of many worlds are both vast and subtle. It challenges our perception of uniqueness. Every choice, every random quantum event creates countless new paths. We inhabit one thread, but others are equally real, quietly evolving alongside our experience. This does not diminish the significance of our actions. It simply situates them within a broader and richer tapestry of existence. Take a moment to consider the philosophical resonance. The many worlds interpretation suggests that reality is far more generous than intuition allows. What seems improbable or impossible in one branch occurs somewhere else. What feels final may be only one aspect of an infinite ensemble of unfolding possibilities. The universe is not a narrow corridor of events. It is a vast, branching landscape, quietly alive with potential. This view also invites reflection on the nature of self. If every outcome occurs in some branch, what does it mean to be me? The self we experience is one thread in a vast web of parallel existences. Other versions of ourselves carry on quietly in branches we cannot perceive, each experiencing its own continuity. The many worlds interpretation does not erase individuality. It situates it within a grand, interconnected framework. Take a moment to imagine gently walking along a path. At each fork, the path divides. In one direction, you continue along one trail. In another, a second you walk along the other. Both versions exist. Both paths are real. The experience of each is complete within its own branch. Yet all are connected through the shared origin of the journey. Many worlds also provides insight into probability in quantum measurement. In traditional views, probabilities reflect our ignorance about which outcome will occur. In many worlds, probabilities describe the distribution of experiences across branches. The universe does not randomly select one outcome. It unfolds all outcomes, gently weighted according to the mathematical amplitudes of the quantum states. Our perception of chance is therefore a reflection of the branches we inhabit, not a limitation of reality. Take a moment to imagine a quiet wave spreading across a pond. Each ripple represents a branch, an outcome, a possibility. The surface of the pond is continuous, yet the ripples manifest the richness of unfolding events. Some are larger, some smaller, but all exist, quietly shaping the overall pattern. The many worlds interpretation also deepens our understanding of time and continuity. Past, present, and future are not singular and fixed. Every moment carries the potential to branch, and the evolution of the universe is a continuous, gentle unfolding of possibilities. The world we experience feels coherent because we inhabit a single branch, but the underlying structure is a vast branching multiverse, ever expanding and quietly intricate. Take a moment to reflect on this calm perspective. Reality is not narrow or singular. It is vast, expansive, and interconnected. Each choice, each quantum event contributes to a gentle, continuous branching that quietly multiplies possibilities. Even though we cannot perceive other branches directly, their existence is implied by the mathematics of quantum physics. The many worlds interpretation invites us to imagine a cosmos that is generous, subtle, and infinitely complex, where every possibility finds a home. Quantum information is one of the most quietly profound and fascinating ideas in modern physics. At first, it may seem abstract, almost invisible. We often think of information in everyday terms: letters on a page, numbers on a screen, signals sent from one place to another. This conventional view of information feels concrete and understandable, but in the quantum world, information behaves in ways that are subtle, gentle, and deeply intertwined with the fabric of reality. Take a moment to imagine a simple message. You write a letter, fold it carefully, and place it into an envelope. The message is contained, ready to be delivered, and its meaning is fixed. In classical physics, information behaves similarly. It can be stored, copied, and transmitted without fundamentally changing the nature of what it represents. In the quantum world, however, information is more fluid, more delicate, more connected to the very state of the system that carries it. At the heart of quantum information is the quantum bit, often called a qubit. A qubit is not like a traditional bit, which is either 1 or 0. Instead, a qubit can exist in a superposition, a combination of both 1 and 0 at the same time. Its state is not fixed until it is measured. Imagine a coin spinning in the air, simultaneously heads and tails, not settling until you catch it. In this way, the qubit carries multiple possibilities, quietly at once, embodying a richness of information that surpasses classical limitations. Take a moment to reflect on this gentle principle. Information is not just stored passively in a qubit, it is inseparable from the quantum state itself. The qubit's position, momentum, spin, or polarization, the properties that define it, also define the information it carries. Change the quantum state, and you change the information. Observe the state, and the information becomes definite. There is a subtle, intimate connection between the state of a system and the content it holds. Quantum information also behaves in ways that challenge intuition. It cannot be copied perfectly, a principle known as the no-cloning theorem. Unlike a classical file that can be duplicated endlessly, a qubit's exact state cannot be reproduced without alteration. Any attempt to copy it disturbs the delicate balance of possibilities, changing the original in subtle ways. This limitation introduces a quiet fragility to quantum information, making it precious and fundamentally different from classical information. Take a moment to imagine holding a fragile crystal. The crystal's structure is beautiful and intricate. Try to replicate it perfectly by hand, and the slightest imperfection alters its form. Quantum information behaves similarly. It exists delicately, maintaining coherence only if treated with care, quietly intertwined with the state of the system and the environment. Entanglement deepens the subtlety of quantum information. When two qubits become entangled, the information is no longer local. Measuring one qubit immediately affects the information in its partner, regardless of distance. This does not violate causality or send signals faster than light. Instead, it reveals a gentle, non-local structure. The information is distributed across multiple systems, inseparable until observed collectively. Even if separated by vast distances, the qubits' fates remain intertwined. Take a moment to imagine two dancers in perfect synchronization. Even if separated across a stage, their movements mirror each other, connected by an invisible rhythm. Entangled qubits are like these dancers. Their states are linked, their information distributed, yet perfectly coordinated in a quiet and orderly way. Quantum information also provides the foundation for revolutionary technologies. Quantum computers leverage qubits and entanglement to perform calculations that would take classical computers far longer. Quantum cryptography uses the delicacy of qubits to create secure communication, where any eavesdropping attempt disturbs the system and reveals itself. These technologies highlight how the subtle nature of quantum information is not just theoretical, it has practical, observable consequences, quietly shaping our understanding and capabilities. Take a moment to reflect on this connection. The principles of quantum information are not just mathematical abstractions, they are active, delicate, and tangible. The ways information is encoded, transmitted, and transformed depend on the soft, subtle rules of quantum physics, gently linking knowledge to the underlying fabric of reality. The study of quantum information also leads to profound philosophical reflections. It challenges our notion of reality as a collection of isolated objects with fixed properties. In quantum physics, information and physical states are inseparable. Reality itself is, in a sense, a tapestry of information, patterns of probability and correlation that define existence at the smallest scales. Observation does not merely reveal these patterns, it participates in their unfolding, gently guiding which possibilities become manifest. Take a moment to imagine the universe as a vast, quiet library. Each book represents a quantum system, each page a superposition of possibilities. Reading a page does not destroy the library, but it fixes the narrative for the observer, while other pages quietly remain, holding alternative possibilities. Quantum information works similarly, containing rich potential that unfolds gently as it is observed, distributed, and interacted with. There is a noise in quantum information also carry quiet lessons. Because qubits are delicate, interactions with the environment, called decoherence, can disrupt their states, scrambling information. Quantum error correction codes have been developed to protect and preserve this information, cleverly distributing it across multiple qubits so that even if some are disturbed, the overall content remains intact. This mirrors the interconnectedness of the quantum world. Information is rarely isolated, but its preservation relies on subtle patterns and correlations. Take a moment to imagine a soft network of threads, intricately woven. Even if a few threads shift or fray, the overall pattern holds. Quantum information is protected in a similar way, resilient yet delicate, interconnected, and quietly self-consistent. Finally, quantum information invites reflection on the nature of knowledge itself. It reminds us that knowing a system fully is impossible without interaction. Information is not a passive truth waiting to be discovered. It is an active property of the universe, intimately tied to the processes of observation, measurement, and entanglement. The act of gaining knowledge changes the very state of what is observed, gently blending observer and observed into a continuous dynamic relationship. Quantum gravity is one of the most quietly profound and mysterious frontiers in modern physics. At first, it may seem almost impossible, even paradoxical. Gravity, in everyday life, feels smooth and continuous. Objects fall, planets orbit, and tides rise and fall. Time and space appear as a stable stage upon which events unfold. This classical understanding, shaped by centuries of observation, feels solid and reliable. But when we look closely at the smallest scales, at the quantum level, this picture softens and becomes far more subtle. Quantum gravity is the study of how gravity, the gentle pull that shapes stars and galaxies, behaves when the universe is reduced to its tiniest components, distances smaller than anything we can directly observe, near the Planck scale. At these scales, space and time themselves are thought to be influenced by quantum uncertainty, fluctuating, vibrating, and resisting the idea of being completely smooth and continuous. Take a moment to imagine a calm sheet of water. From a distance, it appears smooth, reflecting light in a gentle, even pattern. But as you approach, you notice ripples, tiny movements, soft eddies that shift and interact in ways invisible from afar. Quantum gravity suggests that space itself may behave similarly, smooth on large scales, but at the smallest levels, subtly granular, softly fluctuating, and intertwined with energy and matter in ways we are only beginning to understand. One approach to quantum gravity is called loop quantum gravity. This theory proposes that space is not infinitely divisible, but composed of tiny discrete loops woven together in a delicate network. These loops are not rigid. They vibrate, interact, and combine, forming the underlying fabric of space-time. Imagine a soft lace made of countless threads, each thread tiny yet essential, forming a continuous pattern that carries both structure and flexibility. Another approach is string theory. Here, the fundamental components of reality are not point particles but one-dimensional strings. Each string vibrates in its own unique way, producing the particles and forces we observe. Gravity emerges naturally from certain vibrational modes of these strings, linking the familiar pull of mass with the subtler quantum behavior of the underlying strings. Imagine plucking the strings of a delicate harp. The vibrations spread, interact, and resonate, producing patterns that are both gentle and complex, revealing deeper harmonies beneath the surface. Take a moment to reflect on this subtle vision. Gravity is not merely a force that pulls objects downward. It is a dynamic, interconnected property of space-time, responding to mass, energy, and the quantum fluctuations that underlie all reality. Even empty space is never completely still. It vibrates with the soft pulses of quantum activity. One of the most fascinating aspects of quantum gravity is its implications for black holes. Classically, black holes are regions of space where gravity is so intense that nothing can escape. But quantum mechanics suggests that even black holes are not completely isolated. Tiny fluctuations at the quantum level can allow energy and even information to leak out over immense periods of time. This process, known as Hawking radiation, gently transforms our understanding of black holes from static traps into dynamic, evolving systems, quietly connected to the rest of the universe. Take a moment to imagine a dark pool of water. At first, it appears perfectly still and impenetrable, but subtle ripples on the surface hint at hidden activity below. Quantum gravity suggests that space and time themselves have similar hidden layers, where what seems solid and unchanging is actually in constant, gentle motion. Quantum gravity also challenges our perception of time. If space is granular and influenced by quantum fluctuations, then time may also be emergent rather than absolute. Instead of flowing uniformly, it may be softly woven from interactions at the quantum level, inseparable from the structure of space and the distribution of energy. Moments are not rigid points, but intervals imbued with subtle uncertainty, gently shaping the unfolding of events. Take a moment to imagine a tapestry being woven. Each thread represents a tiny quantum interaction. Individually, the threads vibrate, shift, and flex. Together they form a continuous pattern, a fabric of space-time where gravity and quantum effects coexist. Time is not a rigid measurement but a gentle rhythm that emerges from the interplay of countless threads. Quantum gravity also offers quiet insight into the origins of the universe. During the earliest moments after the Big Bang, densities and energies were so extreme that classical notions of space and time break down. Quantum fluctuations dominated, creating a universe that expanded and evolved from a dynamic, probabilistic foundation. This perspective invites a reflective understanding. The cosmos is not a fixed stage, but a living, evolving network, born from the gentle, subtle interplay of fundamental principles. Take a moment to imagine the first moments of existence. A soft pulse of energy, vibrating fields, delicate fluctuations. From this quiet, dynamic beginning, the universe emerges, structured yet flexible, orderly yet full of possibility. Quantum gravity is the study of how these subtle beginnings translate into the vast, majestic cosmos we observe today. Even though we cannot yet directly measure the tiniest scales of quantum gravity, its principles offer a serene and humbling perspective. They suggest that the universe is profoundly interconnected, that forces we perceive as simple or classical are actually emergent from deeper, subtle processes. Gravity is not just a pull between masses. It is the gentle unfolding of space-time itself, intimately connected to energy, information, and quantum fluctuation. Take a moment to reflect on this quietly. Reality is deeper than it seems. The pull of gravity is not merely physical, but woven from the soft fabric of space-time. The universe is not a static stage, but a living, vibrating system, gentle in its continuity, complex in its structure, and endlessly fascinating in its subtlety. Quantum gravity becomes, in this way, more than a scientific pursuit. It becomes a reminder that beneath every force lies a subtle, interconnected network. A reminder that space and time themselves are not rigid containers, but dynamic, gentle fabrics. And a reminder that the universe, at its deepest level, is an intricate, quiet, and beautiful tapestry, softly vibrating with the rhythms of existence, inviting calm reflection and quiet wonder. Dark energy is one of the most quietly mysterious and profound forces in the cosmos. At first, it may seem almost invisible, impossible to grasp. Unlike matter, which forms stars, planets, and galaxies, or light, which travels across the universe revealing distant objects, dark energy cannot be seen directly. Its presence is inferred only from its subtle effects on the expansion of space. And yet this elusive force is thought to make up nearly 70% of the universe, gently shaping the cosmic landscape in ways that are both vast and invisible. Take a moment to imagine a calm, infinite ocean. You cannot see the currents deep below, yet you notice the gentle movement of the water. Ships drift ever farther apart, carried not by waves on the surface but by the slow expansion of the depths. Dark energy acts similarly on the universe, an unseen presence quietly driving galaxies away from each other, stretching space itself with an almost imperceptible force. The discovery of dark energy came quietly, unexpectedly, in the late 20th century. Astronomers observing distant supernovae, exploding stars that act as cosmic mileposts, noticed something surprising. The light from these distant events suggested that the expansion of the universe was not slowing down, as gravity alone would predict. Instead, the expansion was accelerating. The cosmos itself was gently, persistently stretching, guided by a force that no one had anticipated. This subtle observation changed our understanding of reality, revealing that the universe is far more dynamic and mysterious than previously imagined. Take a moment to reflect on this gentle paradox. The universe, vast and ancient, is not merely coasting or gradually settling. It is expanding faster and faster, softly, quietly, invisibly, with dark energy as its guiding hand. Even the emptiest regions of space are not truly empty. They are infused with a subtle pressure, a quiet energy that shapes the cosmic tapestry. One way to conceptualize dark energy is through the idea of a cosmological constant, first introduced by Albert Einstein. Einstein imagined that space itself might have an intrinsic energy, a gentle repulsion that counteracts gravity on the largest scales. Though he initially dismissed the idea, it has returned as a central concept in understanding dark energy. Space is not merely a passive backdrop. It carries energy, softly influencing the motion of galaxies and the evolution of the cosmos. Take a moment to imagine the fabric of space as a calm, gently stretching sheet. Every point on this sheet is connected to every other point. As it stretches, distant regions drift apart, not through movement across space, but because the space between them is quietly growing. Dark energy is the unseen hand, softly inflating the cosmic sheet, subtly reshaping the universe over billions of years. Dark energy also raises profound questions about the ultimate fate of the universe. If this expansion continues, galaxies will drift ever farther apart. Over immense spans of time, stars will burn out, galaxies will grow dim, and the universe will approach a quiet, cold stillness. This scenario, known as the heat death of the universe, is not catastrophic in a violent sense, but softly inevitable, a gentle fading rather than a dramatic end. Dark energy, in this sense, guides the universe toward an expansive, silent future, one shaped not by collisions or explosions, but by the continuous stretching of space itself. Take a moment to consider the subtlety of its influence. Despite its invisibility, dark energy is stronger than gravity on cosmic scales. It is not measured by weight or density in the traditional sense, but by its effect on the motion of galaxies across billions of light years. Its presence is felt everywhere, gently guiding the evolution of the cosmos, shaping the universe in ways that are silent, continuous, and omnipresent. Dark energy also challenges our understanding of physics. It is not yet clear what dark energy actually is. Some theories suggest it is a property of space itself, a vacuum energy that exists even in empty regions. Others propose dynamic fields, sometimes called quintessence, that vary over time and space. Each model is subtle and mathematically complex, yet they share a common theme. Reality at the largest scales is more fluid, more interconnected, and more mysterious than our classical intuition allows. Take a moment to imagine the night sky. Each galaxy is a luminous island, distant yet bound to the vast cosmic ocean. Between these islands, space stretches imperceptibly, carrying them farther apart with each passing moment. Dark energy is the gentle tide, invisible yet persistent, shaping the cosmos without disruption, orchestrating the quiet acceleration of the universe. The study of dark energy also reminds us of the limitations of observation. We see only a fraction of the universe through light and other forms of radiation. Most of the cosmos' dark energy and dark matter remains unseen, yet even in the absence of direct observation, subtle patterns, the motion of galaxies, and the large-scale structure of the universe reveal its presence. This invites a meditative reflection. The unseen can shape reality in profound ways, quietly and continuously, even when imperceptible to our senses. Take a moment to reflect on this quietly, much like the gentle breeze shaping ripples on a lake. Dark energy influences the universe without being directly perceived. It is subtle, pervasive, and profound. It reminds us that reality is often richer and more intricate than our perception alone can reveal. As you continue listening, allow this idea to settle softly. The universe is expanding not merely outward but into possibility. Galaxies drift apart in silence. Space itself carries energy. Time and distance are subtly intertwined with the invisible force of dark energy. Dark energy becomes, in this way, more than a scientific mystery. It becomes a reminder that the larger scales of existence are shaped by forces we cannot see. A reminder that quiet, gentle influences can govern vast structures. And a reminder that the cosmos, at its deepest level, is mysterious, expansive, and beautifully subtle, inviting reflection, wonder, and a soft appreciation for the unseen currents that guide the universe.